Part 3, we have got a mass on a spring undergoing exponentially damped harmonic motion, and we know its period, literally, not literally a period, it's not periodic, but let's say it's the time between times when it goes through its equilibrium going up, maybe. And the amplitude starts at 3 meters when t equals 0, and after 12 seconds, the amplitude is 1 meter. We want to find a model. Okay, so a lot of people get confused by this because, in principle, there's a combination of two things happening. The amplitude is going down exponentially, and there's a sine or cosine oscillation. The main thing is to keep those separate as much as possible. Okay. Um, let's focus on the amplitude. After all, this says the amplitude starts at something. The amplitude, most of this is really about the amplitude, which is an exponential function. Okay, so the full model is a k e to the minus ct, or whatever letters you like to use, times a cosine or sine, but let's just focus on the amplitude. That's really pure exponential modeling, very much like radioactive decay, very much like what we were doing in number 2. Okay, so the first thing is it's nice that we've got data at t equals 0, and so we plug in t equals 0. As always, that gives us a 1 for the exponential and k equals 3. Oh, let's just look real quick at what does this look like in general. Okay, we've got a complicated motion that's a combination of a diminishing amplitude times a sine or cosine, but when we're focusing on the amplitude, it's just this dotted line that we're trying to analyze. And I just broke that out here. I'm really just trying to get a model for the exponential decay that starts at 3 and 12 seconds later it's at 1. That's all I'm focusing on right now. And it's going to be some sort of multiplier times the exponential. Because we know the value is 3 at t equals 0 exactly, boom, that gets plugged in for 3. If you knew it at 2 times that weren't 0, you do have to do a little bit of more math, and that's in one of the other exponential modeling videos that I have done. But we got that value right off the bat, and let's go back. Okay, now we plug in the other value. Okay, so we've got the 3, so this is known to be 3. So our model is 3 times e to the minus ct, and we don't know c, but we do know that when t is 12, the amplitude is 1. So this is the universal thing about modeling. Plug in what you know to find an undetermined parameter in your model. Divide by 3, and notice 1/3, that's a decay factor. The exponential of blah 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 is the decay factor, and we get the unknown constant is ln of this decay factor. It's gone down by a factor of 3 divided by how long it took. Okay, and so it's about 0.09155. So we've got, so that's why I'm skipping ahead just a little bit because it's sitting right here. That's why the amplitude is 3 times a certain decaying exponential. Okay, and then we're going to multiply it by a cosine or sine. Let me go back up. We've seen that there's a way you don't have to use ln's and e's here. We can focus more on the decay factor, the fact that it went from 3 meters to 1 meter, and it took 12 seconds. You can put those directly into the math if you want. The key thing is that decay factor is a factor of 1/3. It's not this minus this, nothing else, nothing like that. It's just that it's going down by a factor of 1/3 in 12 seconds. So that's kind of a third life. So we could say it starts with 3, then it repeatedly multiplies by 1/3. How many times? Well, take the time you've gone, divide by 12, and that's how many times it's gone down by a factor of 1/3. So we could put that in as the amplitude. Okay. Now, one thing that was confusing people, I think, was, hey, where's the 4 seconds coming in? It doesn't come in right now because we're just analyzing the amplitude. We know it's a certain decaying function. We know 2 values. T equals 0 gives you amplitude is 3. T equals 12 gives you amplitude is 1. The 4 seconds doesn't come in here yet at all. Where that comes in is when we actually put in the cosine. Okay, so we have got a cosine of omega times t, and omega is always just 2 pi over the period, which simplifies to pi over 2. So this had to do with the 4 seconds. This had to do with the other data. They didn't mix at all. Now sometimes you'll get a description that purposely mixes them, like, oh, it took a certain number of periods for a certain decay to happen. But here they weren't mixed at all, and you can keep them separate. If you can, keep them separate. Okay, so we could also use the third life style. these really are the same function. You can graph them and see that they're the same if you want. Some people did some funky stuff by really wanting to express it in terms of periods, that 1/4. They really wanted to express it in terms of periods. You can if you really want to, but you get like a weird 1 over cube root. I'm not even going to go into that. I just want to validate that really does work, but it's unnecessarily mixing the two when you're not forced to mix them. Okay. Oh, and I'm using a cosine here because I didn't specify whether it starts in the middle or high or low. So it's not really, I haven't really completely nailed down what it looks like. But if you use a cosine, it looks like this. Starts high, wiggle, 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 wiggle. And this dotted line is for the next part of the problem, where we ask, when does the amplitude, remember that's going to be the envelope function that just goes between the peaks here, when does the amplitude get down to 0.2 meters? Okay, so that's, this is part B, which is right here. Okay, and it says how many cycles of oscillation occur. Okay, so again, that's talking about the oscillation, that's talking about the amplitude, but again, it's really mostly interesting about talking about the amplitude, and we're going to put in that cycles thing at the end. Can you just figure out how long it takes for the amplitude to reduce to 0.2 meters? That has nothing to do with the oscillation directly. Here's the amplitude function in one of the forms we had, the E form. Just set it equal to 0.2. Divide out the 3, take a log, divide by the rate constant. The time is going to be 29.6 seconds. So pause it and go through that if you want. I'm not going to go through the details. Okay, so now we know how long it takes to figure out how many cycles of oscillation occur. All you got to do is divide by the period. Okay, so the number of 4-second cycles that happen in 29.6 seconds is about 7. It's really about 7.5, let's say. I think it's like 7.5, maybe 7.4, 7.6, something like that. Okay, so this can be confusing because people's temptation is to combine them, and in particular, a lot of people want to say, "Oh, I think we're supposed to take the full model here, and set that equal to 0.2." Not really. The amplitude is supposed to be 0.2 meters here, and that's a much simpler question because solving this algebraically is pretty much impossible. Solving this one is not impossible. And then the only place the oscillation comes in is that we are asking the question not in terms of 30 seconds, which is a pretty decent answer, but in terms of, oh, how many bounces? Let's see, 1 full cycle, 2 full cycle, 3 full cycle, 4 full cycle, 5 full cycle, 6, 7, and you're still a little bit past, but then by 8 is definitely not there. Okay, so about 7.5 full cycles before the amplitude is less than 0.2. Okay, definitely a challenging one, but the thing to repeat to yourself is, do I really have to combine things right now? The exponential part and the oscillation part.